Mars without the rockets. But getting from here, when you get to, away from Earth, out of low Earth orbit, onto Mars, that is a huge challenge. And so our next panel, we'll be talking about transit to Mars, how we're going to build the systems, the vehicles that'll be able to transport humans, keep them alive on the trip to and from Mars. So leading this panel is Tim Cichan from Lockheed Martin, and Tim has been a friend of Explore Mars for many years, been a participant in this conference, the Humans to Mars Summit, very active in our Achieving Mars workshops as well for many years. Tim has been at Lockheed since 2002 you started at Lockheed, so some time. And he is the, I can't find your title here because the Space Exploration Architect currently at Lockheed Martin. So, Tim.
All right, thanks, Chris. So, we'll talk about the Mars Transit Vehicle. And to give you an idea of what that might look like, go to the next slide. So the Mars Transit Vehicle it's a space station. It's a big propulsion system. And it's got to be away from Mars and from Earth for so long, keeping the crew safe in times when the speed of light can be up to 40 minutes round trip. So it is really one of the challenges that need to be solved, including the landing part, including the launching part. So at Lockheed Martin, we've got a concept called Mars Base Camp that we rolled out in 2016. And we're actually, because of the risks that the Mars Transit Vehicle needs to take on, we advocate a orbit-only mission first to buy down that risk while you finish developing the lander. So today we've got a great set of panelists. We're going to talk from all kinds of different perspectives on what it takes to design and build and operate a Mars Transit Vehicle. So I'm the Space Exploration Architect at Lockheed Martin, and I lead our early concept design teams to look at human and robotic exploration of Moon, Mars, and the rest of the solar system. It truly is a dream job for me. So why don't we go along and have the panelists introduce themselves? Go ahead, Laura.
Hi, my name's Laura Burke. I'm from NASA Glenn Research Center. I actually started at NASA in 2007. I've done a whole lot of low thrust work since then, but I've since transitioned to working mostly on supporting crewed spaceflight. So right now, I'm actually working as part of the flight mechanics team for HLS, but the reason I'm here is I'm the transportation lead for NASA's Mars architecture team.
Great.
I'm Hoppy Price at JPL, and so I'm chief engineer for NASA's robotic Mars exploration program, and I've had the pleasure in my career of working on missions to the Moon, Mars, Jupiter, and Saturn. And I've also been supporting the HLS program and other human mission activities.
And I'm Seamus Tuohy with MDA Space, the largest space prime in Canada. Most people know us with the robotic arms. I'm in the Robotics and Space Operations group. I am head of business development in the US.
Right, Darren Samplatsky. I'm the business development lead for our deep space portfolio at Aerospace. Been there for, I guess, going on 28 years now. Spent most of my career developing life support and thermal control systems, mostly for NASA. Probably spent the last, 8 or 10 years doing this business development thing. So looking forward to the discussion.
All right. Well, thanks, everyone. So, Laura, why don't we start with you?
Sure. Oh. Okay, so these are some charts some of you might have seen before, but hopefully not too many of you. Basically, I think we've got a good handle on what it takes to go to the Moon. We've done that before. Mars is going to be very different. It's significantly farther than the Moon. Obviously, the Moon orbits around Earth. It's always about 400,000 kilometers away. However, Earth and Mars both orbit around the Sun. So we've got periods when Mars is closer to us and periods when it's 4 million kilometers away. Also, our typical round trip odometer reading when we go to the moon is on the order of 2 million kilometers, whereas if we want to go to Mars and back, it's going to be 2 trillion kilometers. So that makes transiting that vast space really difficult. We need large vehicles in order to accommodate that kind of transit. In addition to that, Mars' gravity well is going to be deeper than that of the moon. So we've got this little graphic here. It's not as deep as Earth's, but it's still about 3/8 that of Earth. So whatever we're trying to use to launch off the surface of Mars is going to have to be more capable than what we're actually going to use to launch off the surface of the moon. Also, typically when we talk about going to ISS, we're looking at mission transit durations of like hours to days, and the moon is going to be days to maybe weeks. But when we go to Mars, we're talking about years, and that's significantly longer than our current experience. Some of the challenges of Mars transit, there are different aspects of it. During the transit, we're going to run into most likely conjunction events where Earth's on the other side of the sun and we can't communicate directly with Earth, and those can last several weeks. So what do we do during those events? How do we plan our CONOPS to accommodate these periods of time where we're not going to be able to communicate with our crew in space for several weeks? In addition to that, we've got the daily challenge of a 40-minute round-trip communication delay. How do you plan and operate a space vehicle or a surface mission when the delay time is 40 minutes long? Getting to the surface, obviously, we've had experience landing smaller rovers on the surface, but now for our human-class payloads, we don't need to land several tons. We need to land maybe 40 tons. So that's a whole new class of lander that we're looking at, and I think some of those concepts have been discussed earlier in the last couple of days. Getting back from the surface, we've only launched off of 2 planetary bodies. We have experience launching many launches off of the surface of Earth to go to ISS, and a couple going to the moon. We've got great ground support, and we've got continuous communication when we're doing launches off the surface of the Earth. We've experienced several launches off of the surface of the moon. The communications delay with the moon isn't nearly as long, so again, we've got really good communication during that. We have no experience launching off the surface of Mars. And how do you launch off the surface of Mars when you've potentially pre-positioned a vehicle that's been sitting there for a couple of years? How do you get that vehicle ready? And what do the launch operations look like when you can't continuously communicate with your crew? So that's another challenge. And then Patrick mentioned it earlier in the week, and it was brought up. Mars aborts. They're not going to look like what we've experienced before. When we're launching off of the surface of Earth, we've got lots of contingencies for if it goes poorly, we can come back. If we're at ISS and we need to come back, we can come back within a couple of hours. If we're at Gateway and need to come back, we can come back within a couple of days, or even on the surface of the moon. It's not a long stretch of time before we can actually bring our crew home. But once you hit that go button and you do the trans-Mars injection burn, you've really made a commitment that you're not coming back for a while, even in an abort scenario. If you hit that button to go and you want to come back a week later you decide we can't do this, it's not going to be, okay, 7 days from now I'm coming back. It's going to be, many days, hundreds of days from now. And at some point during your outbound transit, you're going to hit a point where if you want to abort, it's basically going to take the duration of your nominal mission anyway. So that's another scenario. What do those abort scenarios and those contingency operations look like? So that's going to take some forward planning too. I should have realized these were all click through. Finally, I know all the NASA people up here, we're plugging our white papers. They're small digestible chunks of the challenges that we're facing. So I really encourage you to check them out. They cover some of the topics that I talked about, communications issues, some of our transit, outbound transit challenges and mass challenges. So I hope you read them. They're a little more friendly than the full ADD.
Great.
Thanks,
Yeah,
Laura.
the white papers are great. I highly recommend them.
So Laura, and I remember reading some of those white papers. To be able to do an abort, do we have to use nuclear propulsion, or can we use chemical propulsion for those aborts?
You can use chemical propulsion. I mean, some of our concepts that we've developed, we've looked at all high-thrust concepts. We've looked at some hybrid propulsion concepts that have, a high-thrust system and a low-thrust system. We've looked at all nuclear concepts, and we've looked at some, non-nuclear concepts. You can abort with any of them. Some of them are a little bit more robust to aborts than others. The hybrid has the advantage of, you've got two propulsion systems. So if you have a problem with one of the propulsion systems, you've got another one to rely on fully. But you can absolutely abort with, the NTR type of vehicle or an all-chemical type of vehicle or even a SEPChem or a NEPChem type of vehicle. Those all have abort options.
Thanks. Right, Hoppy.
All right. Let's see, that's a different presentation. No, there we go. Okay, so transit to Mars, we've actually done that many times with our planetary missions. We've sent many vehicles transiting to Mars, so I think we kind of have that down for the robotic vehicles. Of course, we've never done the transit back from Mars orbit back to Earth again, although our Japanese friends hopefully will do that in the relatively near future with the MMX mission coming back from Phobos. So that'll be a great experience and sort of a precursor to Mars sample return missions to follow. So some of the lessons that we've learned from our robotic missions, some of them are in propulsion. And so, Laura talked about different propulsion systems for human missions to Mars, and really all of them are viable in one sense or another, depending on which values you choose in the Mars architecture for the when and the why and all those kind of questions. You can come up with in many different kinds of propulsion systems. So in the planetary missions, there's definitely a trade-off between performance and complexity and the heritage and the cost and the risk. So the main two propulsion systems that we've looked at for the Mars missions are biprop propulsion, which has better performance, and then monoprop, which is lower performance, but it's a simpler system. And so sometimes we choose for the higher performance system because we have to, and other times we go with the monoprop, which is cheaper and simpler, not as good a performance, but it's just the right choice. And so we have two Voyager spacecraft that have operated in space for 47 years, and they have a simple monoprop system. So I'm glad we chose that instead of a biprop system. We've also used electric propulsion for planetary missions, and those are also good for Mars missions too. And one of the lessons learned from that is that you have to take into account the fact that at some times in the mission, your solar electric propulsion system may be down for a time. So you need to put in plenty of margin for lost thrust periods when you have electric propulsion. Telecom, Laura talked about the conjunction issue, and just at the end of this past year, we had conjunction for all of our Mars vehicles. So we have typical plans we do for that, and we got through conjunction just fine. But again, there were no people on board, and we weren't doing a lot with the vehicles during that time. But that worked fine. Some of the other issues that we've looked at are functional redundancy. It's usually good to have more than one kind of antenna, more than one kind of radio frequency system that you're using as a backup. There are times on our rovers where we've relied on relay satellites to get the data back, but sometimes we have issues with the relay satellites, and we've had to rely on the backup of a direct-to-Earth communication that we have. So it's always handy to have more than one way of doing that. And then Laura mentioned the time lag. Of course, that is a considerable issue for human missions. For our robotic missions, we're just kind of used to that. You know, we send up a sequence, and you know we're waiting for it to come back, and you know we're not in a hurry. Although I did work on the Grail mission to the moon, and that was such a treat because you could just operate it in real time. You could send a command, it would come back right away. But for the missions to Mars, that's just not the case. Fall protection is a big issue for planetary missions, also for crewed missions, and there are a number of lessons we've learned from that. You want to keep your autonomous fall protection simple, otherwise you may get into some convoluted fall protection routines where something happens you're not expecting, and maybe it's not something you completely tested for because there's so many branches of the fault tree, and you may get to a spot that really isn't where you want to be from fall protection. So one of our lessons learned is to keep that simple and to do lots of testing on that. But one advantage to crewed missions is that when you have a crew on board, if your fall protection starts shutting down things and you don't really want it to shut them down, you have a crew to override it. So I see that as a big plus. Sometimes I wish we had that on our planetary missions. Sometimes we have in-flight reconfigurations of our vehicles, like we'll jettison ballast, we'll jettison a crew stage. As we come down for a landing, we jettison a back shell. So all these kind of issues where you're reconfiguring the spacecraft, you have different mass properties, different control dynamics. So for the crewed missions to Mars, you'll probably have stages that you're going to jettison. You're going to be deploying some things, maybe retracting them. And so the more you can simplify the in-flight vehicle reconfiguration, I think the better your odds are. And then last but not least is planetary protection. And so we have certain protocols that we use for our planetary missions, and it will be a challenge for the human missions to Mars. And you have to think about all the elements that you're discarding. So if you discard a stage or a back shell and it's going to land on Mars or has a chance of landing on Mars, you have to do all of the analysis and tests to make sure that you're going to meet all the requirements of planetary protection.
Thanks, Hoppy.
Sure.
Yeah, when I started my career, I worked on geosynchronous communication satellites. And so we would do the burn plan and all that. And we tell the operators, okay, hit the enter key for the burn start 2 seconds before the time on the sheet. And that'll take care of the lag.
Yeah. Well, you know, a really interesting mission were the Pioneer 10 and 11 because they didn't have computers on board and it was all commanded. So you had to tell Pioneer 10 or 11 when to do a maneuver, and you had to plan it for the speed of light time, which might be, you know, half a day to get out there, and you basically joystick the thing through a time delay. So I can't believe they pulled that off, but they did.
Wow.
Yeah, Pioneer 10 and 11 was amazing because the technology was so crude, but they made those missions work.
Yeah, so
Yeah.
we'll always find a way to make it work. Seamus.
Sure. So let's see. There we go. First a word from our robotics overlords, sponsors. I'm at MDA Space again, so we have to talk about robotic arms. So several things we've mentioned previously: large vehicle, a reconfigurable vehicle. So one of the things to be concerned about is how do you assemble the vehicle in space if you need multiple launches from Earth? How do you gather things together and make it a system that starts going to Mars? During the transit to Mars, you worry about operations and maintenance. You know, normal operations, reconfigurability. You know, if you have consumables, you know, when you've consumed something out of a module, you know, you maybe want it to get out of the way. One of the problems that a lot of people may not think about is there are only so many ways to put together a vehicle. You know, there are only so many interfaces. So it's probably going to be that this vehicle will have to be reconfigured on the fly, moving things around. And a great way to do that is using a robotic arm. And then the maintenance part, keeping things alive. You know, the way to keep the astronauts alive is to keep the vehicle alive and operating. So we'd like to build on the extensive work that has been done in human space, starting with the shuttle. That's the upper left arm. The current one on station has been operating over 20 years. The Canadarm2, that MDA was privileged to supply both of those. And then we're in development right now for what we call C3, the Canadarm3, which is the Canadian Space Agency's initial contribution to Artemis that will go on the Gateway. And that's what these arms do. They do the operations and maintenance of very large structures in space. So there are a lot of lessons to be learned from that, a lot of operations, things to be learned from that. it's also test beds that you can try things out beforehand, before you embark upon your trip to Mars. So doing things like exterior inspection, repairs, moving things around, doing capture and berthing of visiting vehicles. There may be rendezvous during transit, or as vehicles come back from the surface, or a vehicle comes back from the surface, how to capture them and put them back in place to support astronauts when they're out there, and also the initial in-space assembly. And also the robotic arm itself needs to be able to repair itself. So robots repairing robots. So some of the things that we're thinking about is, EBR systems and IVR systems, so extravehicular robotics and intravehicular robotics. So having robots inside the spacecraft that also do logistics and repair, alleviating some of the tasking that you would have of the astronaut, and robots of various size that could have access to certain parts of the spacecraft that maybe are too big for humans or too buried in the back for humans to reach. You worry about interfaces, tools, things like dexterity, walking between vehicles, walking from the initial assembly vehicle onto the Mars vehicle, if those are different. And the interfaces, making sure that you don't have too many of them, that are too complex, so that you don't have to carry around as many tools on board. Things like advanced perception and intelligence, being able to recognize differences from the last time you were there, or being able to navigate yourself to a position, again, trying to detask the astronauts as much as possible. Diagnostics and self-repair, being able to predict failure, and if a failure happens, using a functional redundancy like Hoppy talked about, to keep going on the mission while you repair it, but being able to detect where the fault is, diagnose, and perform repair. And then finally, the big thing about logistics, a certain strategy of sparing and staging. I talked about leaving vehicles behind, shedding vehicles to eliminate mass, but also sparing. How many multiples of things do you carry on board, knowing that some of them are going to fail? Worry about commonality. Do all things look the same? Do all things fit the same together? Modularity. Can you use a board from one avionics box in another avionics box? And not only printing food, which I heard earlier, which is great, but printing parts, printing tools, printing things so that you limit the sparing that you need to do. And then the mass that goes into that printing, which is feedstock, and maybe going into looking at recycling. So these modules that you use, the consumables, maybe you don't throw them away. Maybe they then become feedstock for future use in printing systems. Is that?
One question, and I know that on ISS, just dealing with the logistics and the storage and moving things around, do you think that there'll be an internal robot in the transit vehicle doing that kind of task?
Sure. I'd like there to be, because a lot of what happens in station right now is that you have astronauts there 24/7, but the amount of time spent, even like unpacking and repacking cargo vehicles, right. Is when we talk about robotics, we talk about robotic systems allowing an increase in time on task for the astronauts. So you'd like to alleviate some of those tasking. Just they could spend their time doing other things. But also, it's not for sure that in this vehicle, this very large vehicle, that humans will be able to access everything. And robots also have the advantage that they don't have to don and doff suits. So you could imagine a robot that would go inside and outside through an airlock that could carry things or reach things that the astronaut would either have to put a suit on or crawl around in spaces that aren't designed for them to crawl around in.
Great. All right, Darren.
We're going to need a way to get the stuff out of the trailer, right?
Absolutely. Or leave the trailer behind.
So I thought I'd talk just a little bit about some of the history and some of the stuff that we've worked with NASA and with a lot of the primes over the last 60 plus years. and really need to incorporate those lessons learned from those programs in order to make this successful, because there's a lot of stuff that we've learned and a lot of stuff that I think we've already forgotten. So Collins Aerospace, which was formerly Hamilton Standard, then Hamilton Sunstrand, then UTES, and now Raytheon. So we've made a lot of name changes over the years, but the same company. We've been working with NASA going back 60 plus years. Started out on Gemini, had a lot of content on the Apollo missions. We did the suit, mainly the primary life support system. And my talk's mostly about life support and thermal control. So we also did the environmental control life support system for the LEM. And so I heard someone talking the other day about Apollo 13 on stage. We were actually part of that team that had to figure out how do we connect the CO2 removal system from the LEM to the crew module. And so there's pictures of our guys in our lab, actually, when they threw all the stuff out on the table. Some of that was our team back in Connecticut. We also did a lot of the life support thermal control on the space shuttle. So lots of systems there that we eventually adapted some of that to the International Space Station. We did the fuel cells on the shuttle as well, and then we did a project called the EDO toilet, Extended Duration Orbiter Toilet. So I think the original toilets were built by GE. Somehow we ended up with that contract down the road, and then at some point we redesigned that toilet, and the toilet that we developed for Orion was actually a derivative of that. So we have lots of toilet history. Unfortunately, we didn't build the toilets for International Space Station originally because it went to the Russians. But we did, about 2 years ago, deliver a flight experiment for a toilet that's actually being tested for Orion. We also did the spacesuits for the space shuttle. So we developed spacesuits that were supposed to be serviced every time they came back. So they would be out for a maximum of a couple of weeks. They would come back, get serviced. We built 20 of those suits. Because of funding constraints, they decided, hey, we're just going to reuse those suits for the International Space Station. We had lost a couple of suits because of issues or loss of the shuttle. So now we have about 12 of those suits left, and we've been, I'll say, upgrading and rebuilding those suits now for the past 20 some odd years. Ryan Scirocco talked a little bit about the next generation suit, the XEVAS suit. So hopefully in the next couple of years we will have that up on station, and then also a derivative of that for the Artemis programs for the lunar surface. Like I said, we've also developed a bunch of hardware for the International Space Station. So we did a lot of the closed loop life support systems, so the water processor assembly, oxygen generator assembly. So that's actually where I started my career with Hamilton Standard was the development of the OGA. We also did another system called the Sabatier, which actually took waste CO2 and waste hydrogen to make water and methane. So I was actually the chief engineer on that for, I don't know, probably 10 years. So, all of these systems that we're eventually going to need for a mission to Mars, we're starting to, I'll say, lose some of the people that develop these systems. So, we're starting to lose some of that corporate knowledge. So I think, now's the time that we start to refocus some of that because we are going to need those systems. We also did a lot of work on the SLS. We do the thrust vector control for that. CST-100, which is the Boeing Starliner. So we did a lot of the life support as well as the thermal control systems for that. So fingers crossed for Friday. Hopefully it takes off this time. No more valve issues. And then, we're also involved a lot with the Orion vehicle. So we're one of the subs to Lockheed Martin. We do the life support for that as well as the thermal control, power management, and then I talked about the toilet already. And then things like deep space transport. So probably back in 2016 or 2017, we actually had a contract with NASA under Next Step Appendix A where we developed what we called modular eclipse. It was designed basically to take what we had done on Space Station and make a modular eclipse system so that we could put it eventually into something like the Gateway or the Mars Transit Vehicle. We worked on that program, I don't know, up until last year. I think we finally ran out of funding. But those are the types of programs I think we need to be doing today in order to keep this momentum going, and so we don't lose that corporate knowledge and that NASA knowledge going forward. The other things that we're currently doing is we are using ISS as a test bed right now. We are doing some upgrades to like the water processor assembly. We have a program called Advanced OGA right now where we're basically redesigning the OGA based on current materials of today. But I don't think we're taking it far enough. We're also doing stuff with additive manufacturing like condensing heat exchangers and those types of things. But these are the programs I think we need to be doing now. We need to build like a test bed someplace on the ground. I laugh, I go down to Marshall Space Flight Center. They have an Eclipse test bed that they've had there for several years, and I look at it, and it's hardware that I hand-built myself 20 some odd years ago, and it's still what they're using today. And it's a shame because we really need to build those systems and start testing now because we're never going to be ready in 10 years like we want to be. And so looking forward to questions.
Yeah, so you mentioned the needing to bring back the spacesuits and do maintenance. Is this one designed for less maintenance?
It is designed for less maintenance. Now, obviously, if we're using that on a lunar surface, you're going to have to deal with things like dust. So, we'll have to have robust systems to clean it. Obviously, on a Mars transit, that's not an issue. So, but yeah, they are being designed to be serviceable in orbit.
All right, great. So I do have some questions for you, and then we'll get to audience questions. So, Laura, what's the trade space right now for how long the Mars transit is going to take?
So traditionally we think opposition or conjunction, but the reality is there's kind of a very large spectrum of times that you can do the transit in between those. And you can always go longer, and you can also always go shorter. But right now, that's how long our mission is actually one of the decisions that needs to get made. It'll be in the decision trade space. So we are trying to design vehicles that would fit numerous transit durations. So there's not just one that we're designing to, or even two. We have to think about long term, like, what does a vehicle look like if we're doing a conjunction mission? What does a vehicle look like if we've got somewhere in the middle? Or what does a vehicle look like with something that looks more like an opposition class mission? So those are not necessarily the same thing.
And what are the pros and cons of short or medium or long types of missions?
So the surface duration is going to be kind of a big driver towards which way you go. If you want to spend 300 days on the surface, you're not going to try to do 300 days on the surface and then fit in an opposition class mission around that. And if you only want to spend 30 days in Mars vicinity, you don't get the benefit of the home and transfer out, home and transfer back. There are pros and cons. Opposition class, that it gets closer to the shorter total duration, so closer to that 2-year time frame, which is a little more comfortable. Thinking, we have about a year experience in space, so 2 years, maybe that's not as scary as 3 years for a conjunction class mission. Conjunction class missions, though, you've got two kind of optimal legs on either side that are rather short, comparing that to the opposition, where you've got one optimal leg and then one much longer leg. So your in-space time is actually longer for those type of missions, even though the total mission duration is less. But you can't make a Mars transit duration decision on its own. Looking at it, it's like, oh yeah, it makes sense. Let's go fast. It's better for the crew, physiologically. It's great. We can get out there, get all of our stuff done, and come back. But in the reality, you start dialing down that duration knob in your vehicle starts getting larger and larger. We like to say Mars is like a balloon animal, so when you start squeezing on one, everything else kind of expands. So yeah, I can make you go really fast, but you might end up with a vehicle that's got significant technology development required for the power and propulsion system, and maybe a whole lot of propellant necessary, or maybe it's pushed you into doing some con-ops that are a little bit riskier than you normally would have. So it's all a balancing act. We're trying to supply concepts that kind of fulfill where we would look at in the design trade space. So whoever ultimately makes that decision has all the information that they need.
Thanks. Seamus, so we talked about internal robotics, but what do you see the external robotics on a Mars Transit vehicle doing? And are we going to be able to now just, instead of joysticking it, will the crew be able to say, hey, Canada Arm 4, go replace this solar panel?
Well, I'm glad you said Canada Arm 4. We'll see. So the first thing is there's a vehicle now on the screen. That vehicle will have to be assembled, and so it makes sense that the arm or the arms that are used to assemble that vehicle then walk on the vehicle and spend their life with the vehicle in transit. And you can imagine the vehicles would have to be able to walk around like they do now on station, whether it's through a shuttle mechanism or actually physically, end-to-end walking. They'll have to be able to have a reachability so that they're designed to reach anything and everything externally on the vehicle. You would think that the one place you wouldn't reach would be the place that you're going to have a problem. So you want it to be to reach everywhere. You need a set of tools, end effectors that can do the work not only that you plan on, but repair that you may not expect for it to do. You also need it to assist the astronauts. Right now on station, the astronauts are assisted by the arm. They ride out on the end of the arm, and it moves them around the station. But the big thing, I think, is you look at this configuration, and it's an end-to-end one. Everything is kind of in line. You would think that things are going to have to move and be repositioned, during the vehicle life, and things will come off the vehicle when you get to Mars. Things will go down the surface. Things will come back up. Those have to be rejoined in a way and reconfigured. So the arm, and I'd like to use plural because there'll be some larger arms that move a lot of mass around. There'll be smaller arms that are more dexterous and can get into smaller spots, but they'll have to link together. And to answer your final question, instead of it being something where the astronaut says, move to this, you would think the intelligence on board would be able to do it while the astronaut's not even paying attention. And what I'm talking about now are routine things. There'll be a lot of time, so I'm sure the astronauts will have time to do things which are out of the ordinary, but a lot of the routine stuff, the day-to-day stuff that you would expect that the robots could do, just like they do on terrestrial in factories and things like that. They do a good job of assembling cars and assembling even satellites now. So there'll be a host of operations that they do automatically, and then there'll be a way that intelligence built into the arms and the end effectors will be able to alleviate a lot of the low-level decisions that a crew would have to make, enabling them to get higher in what they perceive, what they have to perceive, what they have to command, what they have to take care of, and contingencies, things like that.
Great. Yeah, and this is the nuclear thermal propulsion configuration of Mars Base Camp, and you can see on the left side that there's an arm right there in the picture.
Yeah. I also see there's a nifty space plane too. That's nice, right?
Yeah. And I can't imagine what it's going to be like to be in that suit on the end of an arm in orbit around Mars. That's great.
I just hope you don't have a fear of heights.
Yeah. So, Hoppy, based upon your Mars experience, what technology hurdle is out there that you want to make sure is addressed? Maybe we're not thinking of.
So, there's the technology issues that we've had with the robotic missions, and I don't really see those being the big concerns for the human missions. To me, I think the biggest concern is the life support system. Yeah. And of course, that's something we don't have on the robotic missions, but to me, that's one of the biggest problems to solve, to have the reliability and, the optimal amount of resource reusability to try to decrease the mass, but not make it so complex that it's going to break, so it's going to be the sweet spot between reducing mass, but also having it be simple and easy to maintain, and of course, highly reliable.
Yeah, and I think that interaction between reliability and then therefore how much spare parts you have.
Yeah, right.
And how closed loop versus not quite closed loop. So that was one question I had for you, Darren.
Yeah.
Like how close to closed loop do you think we need to get?
So, I'm not sure we'll ever get 100%, right? But, right now on space station, we're somewhere around 88%, which is pretty good, right? I think NASA's goal, and they did put the brine processor up there, so Paragon, Grant Anderson was out here the other day, that's their system. They got that up there, that increased our water recovery, so having systems like that in place are great. But I'm not sure we'll ever get to 100%. NASA would like to see like oxygen recovery at something above 75%. With Sabatier right now, we're probably around 50%. So there's things that we can do to get closer, but at the end of the day, you're really talking thimbles of water. It's not huge amounts. So can you pre-position supplies out there so that I don't need to rely on these systems for everything. I think they're going to have to do some of that in order to be successful. So yeah, I think you want to get as close as you can, but you're probably never going to get to 100% closed loop life support.
All right, thanks. Questions from the audience? We'll come on up to the mic.
So, Laura, I just finished reading the MTAS studies, which are great, but looking at the trade space for EP, whether it be SEP or nuclear electric, or it be solar electric propulsion or nuclear, I keep seeing that hybrid element being brought in. Can you talk about how, hybrid components might offer more options or solutions in a DST trade space? Thanks.
Yeah, so like I mentioned when we were doing the introductions, I've done low thrust work for a long time. And so I've really seen the benefits of it. And I mean, when we've looked at Mars, and you traditionally think of, missions to Mars, it's, one big rocket, you hit a button and it's a large burn, and then you coast and you get to Mars and the engine turns on again. But in between those two burns is 200, 250 days, we're not doing anything. If you have an EP system on board, it really helps you soften those really inefficient high thrust burns with some ultra efficient EP in the middle. So you can actually reduce the TMI burns and the MOIs and the TEIs and the EOIs, sorry, lots of acronyms. All of those traditional high thrust burns can all get shrunk a little because you're providing that acceleration with your highly efficient EP system. So you take that 200 and some days that you would just be sitting there, and now you've got your EP system at 3,000 seconds ISP providing your acceleration. I think I want to say it reduced our chemical delta V by about 2/3. So it's really quite remarkable what it does. And it fits a lot of It can fit in a lot of different areas too. You mentioned we've combined it with nuclear reactors to do NEP chem vehicles. We've combined it with solar arrays to do SEP chem vehicles, but it doesn't have to just be that. You can combine it with NTP and do bimodal. So I've looked at that before too. I'm a big fan of all of those. So yeah, I keep trying to stick EP in wherever I can.
Go ahead.
Hello, I'm wanting to know if you have a current capacity wanted for this transport vehicle, or is that a decision that's going to be made further down the road?
Current,
Didn't follow that.
yeah, well, current capacity,
Is there a current wanted capacity for the transport vehicle,
Or
or has
volume
that decision not
capacity?
been made yet? Yeah, like crew.
Like how many crew?
How big is it? How many crew?
oh,
Okay.
How many cubic meters? I don't know, yeah.
Crew number is in the trade space. The number of crew that we send out there, the number of crew we send to the surface, those are all decisions to be made. So, we can make guesses and do our reference vehicles just to get an idea of how those systems perform. But ultimately, the number of crew that gets sent out there is a decision far above my pay grade.
Thank you.
and when we looked at Mars Base Camp, we assumed 4 crew. Orion has 4 crew. We based that lander on Orion systems. So and I've seen everything from 4 to 6. I've seen papers on let's send 30. But I think it's sort of in that 4 to 6 range.
Yeah. So like for each crew member that you add, like how many tons of stuff do you have to bring along for resources, food, oxygen, water? It'll add up.
Yep.
Yeah, I think for a crew of 4, the food is about the volume of this stage. So it's
It's a lot. We've got a lot of logistics that we bring to support people for that number of days in space. So maybe the 30 crew will come like later when we've got like the operations and everything down pat. Maybe slightly less than that
Starship
for the
can
first
hold
couple.
hundreds, so.
Right. Go ahead.
For this trip out to Mars and back, have we talked about how the radiation protection might be taken care of? Is that an active or a passive? Is that a problem? What kind of impacts are expected in that duration mission?
Someone want to cover?
Yeah, so I mean, we've studied some active systems for reducing the impact of solar radiation, but they take a lot of energy, so you need a lot of electrical energy, and so those are difficult. So I think that for the first missions to Mars, it will only be passive radiation protection. And it's important to note that there's 2 kinds of radiation. One is the solar radiation, which we're pretty familiar with, and that doesn't require a lot of shielding unless there's a solar flare, a coronal mass ejection, in which case most transit vehicles plan to have like a safe area that's kind of where you huddle up for a couple of days till the flare passes and you have a lot of shielding in that area. But the solar radiation, it's practical to shield against that. The galactic cosmic radiation is like really heavy ions that are going very fast, and they're also called cosmic rays. Those are really not practical to shield against for a mission to Mars. It would require huge, massive shielding, like a couple of meters thick, and I just don't see us having the capability to carry that kind of shielding around, and I've not seen any real practical designs for active systems to deflect the galactic cosmic radiation.
And what we did on Mars Base Camp is that you can't see it, but there's a habitat in the middle of the shiny hydrogen tanks.
Yeah.
And this hydrogen
Yeah.
is such a nice-
So hydrogen and water, those are all great for shielding the solar radiation. And if you had a couple of meters of water, that actually does a good job for the galactic cosmic radiation. Yeah.
If folks have questions, come on down to the mic. It's just one mic, I think. But I did have a question. So we've got a lot of time that will be in transit. We'll be in a new, deep space environment. I think that we're all thinking about, hey, we're going to be doing science on the way there and on the way back. Is that part of the plans? And what kind of science do we think that we could be doing?
Okay, I'll hazard some ideas here. I mean, I think the main science will be the human life sciences and psychology issues. But as far as like planetary science, astrophysics, yeah, there are people thinking about things that you might be able to do. You do have parallax with the Earth for making some kinds of observations. So yeah, I think we'd be looking for ideas for ways to take advantage of being in deep space, away from the Earth, away from other observatories, to maybe do some astrophysics type work. Might be some particle physics kind of work that you could do for science.
Great. What about cracking open those samples on the way home? Do we think we want to do that?
Yeah, I don't think the scientists who want to get the samples back on Earth are too enthusiastic about having people that aren't them opening it up and messing things up.
What if they're
They
on
don't
the
want
trip?
any fingers in their Mars rocks before they get back.
Yeah, and that also has planetary protection repercussions too when you break open the samples.
Good point. So, do we think that the transit vehicle is going to be a single vehicle, or do we think it's going to be, systems and logistics and those sorts of things?
I know it's going to be more than one element.
Okay.
In terms of, is it multiple vehicles? I think that depends on ultimately what in the why and the when decisions. Like if you want to go soon and you want to go fast, that might necessitate, different ConOps with, pre-positioning vehicles. If you want to go slower and you don't want to necessarily go very soon, so you have lots of technology development time, you might be able to, put it all in a single, combine elements to make a single vehicle. But I mean, Mars is very far away and very hard to get to because it's so far away. Capturing into orbit is not easy. Making one vehicle that fits in a single launch is probably unrealistic for something that's crewed. For all of our references, we've had, multiple elements coming together to make one vehicle that the crew then rendezvous with. So that's kind of what I see.
Bob has a question, we're in trouble.
Easy question to make up the rest of the time. The 2033, I guess Mars and Earth going to be closest. Do you see that as playing a major sensitivity in the design of your Mars transit vehicle, or an opportunity to look at maybe sending more than one?
Are you talking about the 2033 opportunity
Yeah.
for Mars?
33 opportunity.
Well, my personal opinion, having advocated for an earlier mission to Mars and a minimal mission, is that at this point, the 2033 opportunity is kind of, the train has left the station. I don't think we have enough time to pull that off, but some colleagues at Boeing and other people have proposed 2035. There is an opportunity for a flyby mission to Mars and Venus. It's a 1.5-year duration. So I think that could still be possible, but that would only be if Congress decided it's really important for us to do this mission, be the first to Mars and Venus, and provide lots of generous funding, very soon for a 2035 mission. I mean, if that doesn't happen, then I think 2035 would be off the table.
You'd also like to have a transit vehicle which is kind of robust to the different types of opportunities. And so I wouldn't design one that would be specifically for the 2033 opportunity because it couldn't do the next ones. And so part of your question was what impact would it have to the design? I think you have to kind of design for what you think is the nominal case, so it's usable for more than just one type of alignment.
Yeah, our reference vehicles, when we look at designing those reference vehicles, we don't just look at a single opportunity, we look at a range of opportunities. We focused on 2039, which is one of the harder opportunities, but we don't, exclusively use that as a reference. We look at, a series to make sure, if we can do this one, can we do all of these other ones too? You don't want to, design something and then say, well, it can only do a third of the opportunities, so don't go those other years.
Have we already decided on what the planetary protection thresholds are going to be for Mars, or is that still being discussed? How much junk can we live there?
Planetary protection is still a decision to be made. Number of samples, all of that, that's all still in the decision-making framework. I think that one's, the planetary protection one, I think is kind of higher on the list though. Doesn't have a lot of flow downs into it. So could be something that gets decided sooner in the decision-making process.
And Hoppy, what do we do right now for the robotic spacecraft?
For the robotic spacecraft, so stuff that we send there, we have certain protocol for cleaning so that we're not contaminating Mars with our biota, but there is a certain amount that is allowed, realizing that even if the vehicle breaks open, the UV radiation and galactic cosmic radiation is going to kill all the stuff over time. What was more difficult for us is for Perseverance, when we're collecting samples, we want to make sure that when we bring those samples back, there's no Earth biota in it, so that when we open it up, we're confused, saying, oh, well, here's a critter here. Did it come from Earth or did it come from Mars? So we do all this genomic sequencing and sampling so we know what kind of stuff was in the clean room that might have gotten in there. But also we had incredible cleaning standards for the adaptive caching assembly, all the robotic arms, all the stuff that handles the samples, the sample tubes themselves. And so the criteria was to have less than one organism in that, and we actually believe that we achieved that. There was all kind of verification done, so it was an amazing effort. I couldn't believe that it was pulled off, but yeah, everything was just immaculately clean for that. But for the human missions, you're sending people there, they're going to be exposed to Mars dust. There's just a lot of questions to be answered. I think bringing back our samples from Mars before humans go would help answer some of the questions about what's there, if there really is a concern.
So we got to send really clean astronauts.
There you go.
Genetically modified, very clean astronauts.
Almost robotic.
Yeah, right. So unfortunately, that's all the time we have for today. But as you can see, Mars transit is challenging, but we're working on these things right now. We've got the Gateway, we've got the International Space Station, we've got propulsion. And so I think I see the path, and there's nothing impossible there. When it's time to go build that transit vehicle, I think we'll be ready. So thank you all.
Thank you.